Dear students, I welcome you to today's session on isometric projection. So before going for isometric projection, let's have a brief introduction about what are different types of projections. And projection, basically it's for two types. One is orthographic and pictorial. And all along you have been studying about orthographic projection, wherein the image of an object is being projected onto a plane. Because you cannot have a 3D object and then give it as such and represent it. It needs to be projected onto a plane or a paper or whatever it is. So when you project it like that, it's going to be only a two-dimensional image. And that is one thing. And second thing is, when you want to do orthographic projection, you keep an object in one position and you look perpendicular to that and project it onto that. So that is what is orthographic projection. So for example, if I ask you what this is, what will you say? So I have drawn two squares of side 50, and if I ask you, probably you will say, sir, this is a cube of side 50. So you are able to say it is a cube because you know you are engineers and you know what engineering graphics is. But if I show this diagram to a non-engineer and ask him what this is, probably they will say, sir, there are two squares. Why? Because they don't have the imagination or they can't visualize it as a cube. So instead, if you want to explain them it is a cube, you have to show in a different projection so that it looks like a cube. So it will be on the paper, it will be on a 2D plane, but still it will look like a cube. That is what we call it as a pictorial representation, because one side, we engineers, we always deal with orthographic projection and 2D drawings, whereas on the other side, the customer or the end user, is more concerned about how the product will look like. So that is where you have your pictorial projection, where you give a 3D representation of it. So in this pictorial, again there are three types. One is axonometric, oblique and perspective. And again under axonometric you have three types. One is dimetric, trimetric and isometric. Of course we are not concerned about these two things because our syllabus revolves around isometric projection. Of course oblique, again it's not concerned about the syllabus, whereas perspective projection will be dealt later and it's a separate topic. So with this introduction, we will know how to create an isometric view of an object. So for example, if you take this cube, right? So in case of orthographic projection, what you do, hold it like this face is perpendicular to you or the viewer, and when you project this gets projected onto the paper or this plane and it looks like a square. But then it doesn't give me any additional information about it's only a square. So I want to know whether I can add some more details to this. So what I do is, instead of holding it like this, I slightly tilt it to my left, or to your left, sorry. So when I tilt it, you are able to see the second face of the cube. So to how much distance should I tilt this, or to what angle should I tilt this? So as I keep tilting, there will be one position in which you will be able to see maximum of these two faces. So if you look at that angle, these two faces will be equally inclined to your vertical plane, or it will be inclined at 45 degrees to your vertical plane. So you are able to see two faces. Next, so I am interested in knowing that more about this solid. So I am seeing only two faces. Can I add one more face? So what I am doing, I am resting here, I am tilting it towards you. So when I tilt it, you are able to see the third face also. Right. Now as I keep tilting, I am able to see this and the three faces. And to what extent or to what angle do I tilt this? So at one particular position, you will be able to see the maximum of the three faces. And that is the isometric view. And in that position, if you observe, the solid diagonal which connects this corner with the bottom corner here, the solid diagonal will be perpendicular to your vertical plane. In this position, what you see is the isometric view or isometric projection of the cube, right? So I told you the isometric view of a cube can be obtained when the cube is resting on one of its corner and its solid diagonal is perpendicular to a vertical plane. Now we will see how to obtain this orthographic view of this. So initially when the cube is kept like this equally inclined, and you look at the top view, it will be like this. So these two edges are equally inclined to the vertical plane. Now the front view of this is you have these two faces of the cube equally inclined to your vertical plane. This is the top view of this, and this is the front view of the cube projected. And the next step, so here you can see the solid diagonal 1 dash and C dash is the solid diagonal. And now the next step, we are tilting it such that the solid diagonal is parallel to the horizontal plane, right? So it will be like this. So the top view, the front view, and finally you are tilting it like this. And then and this is the top view of that. So finally what we are doing, we are tilting it like that so that this solid diagonal, this and this is perpendicular to your vertical plane. So what you have done, initial top view and front view of the cube, and 1 dash C dash is the solid diagonal which is parallel to a vertical plane. When it is parallel to the vertical plane, the solid diagonal will have its true length. And the next step, we are tilting the cube such that the solid diagonal 1 dash C dash is parallel to your horizontal plane and projected, and you get the top view of this. So in this you can see you have the solid diagonal 1C. And finally we said this solid diagonal should be perpendicular to your vertical plane. This 1C will be perpendicular to your vertical plane. So what I have done, I have tilted this diagram such that this 1C, which is parallel to your vertical plane, now has become perpendicular to your vertical plane. I have redrawn this such that 1C, that is the solid diagonal, is perpendicular to your vertical plane. And finally you get the final front view. And here you can see, you are able to see the cube, and this is actually the isometric view of the cube. So you have the top face ABCD. When you see from the top, this face is visible to you. So this is darkened, and the bottom you have 1 is behind, and you have 2, 3 and 4. So this is the concept of isometric view. Now, so generally what happens when you have an object, so for example, when you have this square, when you look perpendicular to this, what you see is the true shape and true size of this square. But when you look at the same square at an inclined position, either you look at it at an inclined angle or you tilt the square. And when you tilt the square, what will happen? Will the square be still a square? No, it won't be a square. Only when you look perpendicular to it, it will be a square. The moment you tilt it, the shape of the square will change. And when I hold it like this along the solid, the diagonal, now it's like this. When I tilt it, when you see from the front, what will happen? This will not be a square. What will happen to the square? Right. So it will be now a rhombus. Right. So again, when you look at an object from an inclined angle, will you get the true length of it? Right. Say for example, you have a straight line here. The line is parallel to your vertical plane. And when you look from the top, what will happen to the length of this line when you get projected here? The length will get reduced. To what extent will it get reduced? That depends upon the angle of inclination. When the angle is more, the length will be reduced. When the angle is less, the length will be slightly different. So like that in isometric view, because you are tilting it, so the length will not be the true length, it will get reduced. And to what extent it will get reduced, we will just arrive at it. Now coming to this diagram, here you have A, B, C and D is the top plane of the square, right? And here you can see that. And because you have the two faces of the cube inclined to a vertical plane, here you can see this is not horizontal, it's all inclined towards it. So again, in case of a square, you have 90 degrees. Because it's a rhombus, these corners will not be 90 degrees. Instead, it will be 120 degrees. So when these two are 120 degrees, and obviously these two will be 60 degrees each. And the solid, the diagonal BD, since it's horizontal or parallel to your vertical plane, the length of this diagonal BD will not change. So this is 120 each because it's a rhombus, this is 60 degree each, and because we have a diagonal here, this will be 30 degrees. And now, keeping this BD, that's a diagonal fixed, we'll actually draw this square, actual square of the actual size. So now we have E, B, F and D as the square, and obviously here it will be 90 degrees because it's a square. Now if you look at this portion, what has happened is BE is the actual length of the square or side of the square, whereas in isometric projection this BE, what has happened, it has come down to BA, and now we need to check whether BA, BE and BA, will they be equal? It will not be equal because BA will be less than BE. By what proportion or what ratio will it be lesser than that, right? So now we will take these two triangles BOA and BOE, and this is 30 degrees and this is 45 degrees. So if you take this triangle BOA, in triangle BOA you have BA by BO, that is BA by BO. So that is 1 by cos 30. Similarly, you take this triangle BOE, in which you have BE by BO is equal to 1 by cos 45. So now from this we need to find out what will be the ratio between the isometric length to the true length of the object. So this isometric ratio is isometric length to true length. So here the isometric length is your BA, which is the reduced length, so this BA, and the actual length is BE, that is the length of the square. BA by B equal to, you have this is BA is equal to BO by cos 30 and BE equal to BO by cos 45. When you apply that here, you will get cos 45 divided by cos 30, and when we get the values, you will get 0.815, and which is approximately taken it as 0.82. So this means the isometric ratio is 0.82, means let's assume if the length of the square is 1 unit and the length of this isometric view of that length will be 0.82 units. So that is the ratio. So of course 0.82 is mathematically, we have a number, and whenever you want to calculate the isometric length, you can always multiply it by the factor of 0.82. But in engineering graphics, you are not supposed to calculate anything, rather you have to construct everything geometrically. In that case, how do I get the isometric lengths of various other true lengths? So now if you look at this diagram, this BA, this is a right angle triangle here, and this BE has been reduced to BA. So what we will do is, we will take this and put it separately here. So there is a horizontal line, and I have drawn BA, which is 30 degrees inclined to the horizontal, that's what we had there. And similarly, we have BE, which is inclined at 45 degrees to the horizontal, and this BE is the true length, and this BA is your isometric length. And how did we get it? We drew a perpendicular from the point E downwards, which will cut on this line BA. So this is my true length and this is my isometric length. Say let's assume in this case, say this true length is equal to 100 millimeters, and what will be the isometric length? So of course you can measure it using a divider, and definitely we should not calculate it using the formula, the factor 0.82. So let's assume now I have a length of 50 millimeters. So how do I get the isometric length for 50 millimeters? So half of this, let's assume this is half the distance. So this is 50 millimeters. That's a true length, say 50 millimeters. Now I take 50 millimeters and mark here, and then from that point drop a vertical line. Now when I measure this distance, it will be the isometric length of this true length. So then you might ask a question, sir, how many times do I do all those things? So basically in engineering graphics we are going to deal with the prisms and pyramids where you have only two dimensions. If it's a prism, it's the side of the prism and the height of the prism. In case of a pyramid, it's going to be the side of the base of the pyramid and the height of it. Only two dimensions you are going to use it, be it even a cone. It's only the diameter of the base and height of the cone. If it's a cylinder, radius or diameter of the cylinder and height of the cylinder. So you have only two dimensions for which you need to find out the isometric line. So once you find out that, then you can do the rest of the things. So this is how you need to geometrically construct this, right? So now you observe this diagram. We have CB, CD and C3, three connecting lines which are joining at C, and these three lines are 120 degrees each, right? So these three lines are called isometric lines. So I'm sorry, that's isometric axis CB, CD and C3. And now if you look at the other lines, say for example you have 3, 4, or you have BA, or you have 2, 1, 2. So all these lines are parallel to this CD, and if you take B2, and this B2 is parallel to your C3, or your D4 is again parallel to your C3. So you can see the vertical lines are all parallel to one another, and these inclined lines are all parallel to one another. So these are called isometric lines. So the lines which are all parallel to the isometric axis are called isometric lines. Right? So the lines which are all parallel to the isometric axis are called isometric lines. And now there may be a line which is not parallel to any of the isometric line. So of course we will see that later, but still, if a line is neither vertical nor inclined here, it's called a non-isometric line, which will not be parallel to the isometric axis or isometric lines. So we'll call them non-isometric lines. And next, if you look at this, as we discussed in the beginning of this session, if you take a cube in one particular position, you are able to see three faces of the cube. Now we will see. So you have three faces, 1, 2 and 3, and these are called isometric planes, right? So suppose I am looking from here, looking from this direction, this is my isometric plane front, and this will be isometric plane right, and this will be isometric plane top. And similarly, if I am going to view from this direction, then this will be my isoplane front, isoplane left and isoplane top. So this is important because later on you are going to have a topic wherein you will convert isometric drawing into orthographic drawing, wherein you have to use this concept of isometric planes, isoplane or isometric planes. So these are the few terminologies which you need to remember: isometric axis, isometric lines, which are the lines parallel to your isometric axis, and there are certain lines which are not parallel, they are called non-isometric lines. And finally you have isoplanes, and in case of a cube there will be three isoplanes: isoplane right, left and then top. The front and depending upon from which direction you are looking at it, either this could be a isoplane front or this could be a isoplane front. Right. So now from the earlier diagram we have extracted this. So this is a partial rhombus and the inside is 120 degrees. So now with respect to the horizontal, because it's 180 degrees, this is 120 degrees, so it will be 30 degrees on either side. So from this clearly you can see that the horizontal lines, because in case of a cube you have horizontal lines, the horizontal lines will be inclined at 30 degrees here, and this you can see the vertical edge of the cube is vertical, it has not changed its shape or orientation. So this is what two things which you have to remember: the vertical lines will remain as vertical lines, the actual solid and the isometric both, the vertical line will remain as a vertical line, whereas the horizontal lines will be inclined at 30 degrees. So this is applicable for when I say horizontal lines, these are all isometric lines will be inclined at 30 degrees and this vertical line will remain vertical. This we have to keep in mind. So now the next question is, I told you that the isometric projection of a cube or any object for that matter will be of a reduced size and the ratio also be worked out as 0.82 times actual size. Then the next question is, sir, a cube is a simple solid where there are only 2 dimensions. So when there are so many dimensions, do I need to calculate the isometric length for each and every dimension? Will it not be time consuming? It's a good question because the objective of isometric projection is to get a 3D view of the object, where I am more concerned about the shape rather than the size. So it can be not necessary that it should be a reduced size. So that is where you have this terminology, isometric view and isometric projection. When I say isometric view, it will have the actual size, and when I say isometric projection, it will be of reduced size. So in the examination, you have to be very careful about this term. When the question says isometric view of a solid, then take the actual size. Or if the question says isometric projection of a solid, cube or a pyramid or a prism, then you need to calculate the isometric length and then construct the solid. So this is one thing you have to remember. The isometric view is your when I say isometric view, it's the actual size. When it is isometric projection, then it means so this one thing you have to remember. So now with this introduction, we will see that how to draw the isometric view of